Hello, in this video, let's look at the RC delay model for a transistor. So we need to model to understand the CMOS logic function, and we need something which is very easy to replicate and compute. Generally, delay is defined as the difference in time when the input crosses 50% of VDD and the output crosses 50% of VDD. So when you use the delay definition in this format, basically if you have a cascade of gates, then since we have the same point where we're measuring delay, we can calculate the delay across a cascade of gates as just the sum of the individual gate delays. So we need to basically define a model that is simple, easy to compute, and gives reasonable estimates of the delay. So one of the easiest models that we use is known as the RC delay model. So let's consider the inverter here. Now when the output is falling, that is when you apply Vin as VDD, the NMOS turns on, the PMOS switches off, and the NMOS discharges this load capacitance. And we know that this capacitance at the load has an intrinsic and has an extrinsic component, and these intrinsic components are essentially nonlinear and time dependent. But we see that this capacitor is discharging through the NMOS, so we can sometimes model this NMOS as a resistor. Now remember, in reality this resistance is actually changing as a function of Vout. So if I talk about the resistance of the NMOS during pull down, the resistance is going to be given at any point by Vout divided by IDS at that point, right? And IDS of the transistor changes as the transistor starts off in saturation and then moves out of saturation. So at any instantaneous point, the resistance for the NMOS is given by Vout by IDS. And if I average this over the entire transition of the output node, then I get what is known as the equivalent resistance of the NMOS. Similarly, I can compute an equivalent resistance of the PMOS during the pull-up transition. So what I'm trying to think about, or what I'm trying to develop, is instead of always invoking the nonlinear IV models of the transistor, can we somehow approximate this capacitor charging and discharging as a single pole circuit whose resistance is determined by the transistor that is connected to the capacitor? So that's why we come up with what is known as a switch model for the transistor. So here is shown an NMOS with three terminals, the gate, drain, and source. This is modeled for switching purposes alone as a resistor with a switch. So this switch, for an NMOS, this switch will be closed when the gate is VDD and will be open when the gate is 0. Additionally, remember the drain and source have capacitances because there are the reverse bias PN junctions there, and the gate has the gate capacitance. So we model this as a gate capacitance between gate and source, a capacitance at the source node, and a capacitance at the drain node. So typically, to use this model, we calculate the value of the resistance for the smallest transistor that can be drawn in a technology. Furthermore, to keep the model simple, what we do is we assume that the capacitance in the gate for that smallest transistor is the same as the capacitance in the source and drain. So therefore, all these three capacitors have a value of C, and this resistance has a value R. So the values of R and C completely determine the switching properties of the NMOS. Again, let's look at the NMOS and PMOS in any given technology, and let's see how this model changes for different widths. So in digital logic, for minimum area and maximum drive, we normally use transistors with minimum gate length. So typically we'd use the NMOS with the smallest gate length available in a technology, the PMOS with the smallest gate length available in the technology. So for that minimum width device, where W is equal to W min, in the NMOS, the resistance is treated as R, and the C gate and the diffusion capacitances in the NMOS are both given by C. The intention of this model is to keep it simple and keep it compute friendly. The holes in the PMOS have a lower mobility than the electrons. So for the same voltage, we expect the PMOS to show lower current. So roughly in silicon, so for the same voltage transition at the PMOS, we expect the resistance to be roughly twice that of the NMOS. Right? So in this case, for the smallest PMOS transistor, we'd assume the resistance is twice the resistance of the smallest NMOS. And for both the capacitors, that is the gate and the diffusion capacitance, we'll still keep it unchanged at C. So the basic difference between the NMOS and the PMOS is essentially the mobility difference, which causes a higher equivalent resistance for the PMOS. So if I want to match the PMOS resistance, essentially I'll have to use a PMOS which is twice the width of the NMOS, which is what we had used when we constructed an inverter for matching rise and fall delays. Now let's assume that we have created another NMOS whose width is K times the minimum width. So in many current technologies, this K is a whole number. In older technologies, this K can be any real number. So now if you look at the NMOS, when you increase the width of the NMOS, for the same voltage, the current in the NMOS is going to go up, right? And the current roughly goes as the same proportional to the width of the NMOS. So if I double the NMOS width, the current is going to double. If I triple the NMOS width, the current is going to triple. So therefore, the equivalent resistance of such a wide NMOS, instead of being R, is now going to be reduced by K. So hence the resistance of the NMOS is now R by K. When I increase the width of the NMOS, I'm increasing the capacitance area at the drain and at the source. Hence the capacitances of this MOS rise linearly with K. So the capacitances become Kc and the resistance falls by K. So when I think about a PMOS whose width is drawn to be K times the minimum width of the PMOS in a technology, its resistance is going to be 2R by K. So this ratio between the NMOS and PMOS resistances continues to hold because we still assume that the mobility is lower in the PMOS compared to the NMOS, and the gate capacitances in the wider PMOS transistor rise up by Kc. And so larger widths, essentially, while they give us larger drive currents, they also increase the intrinsic capacitances that are associated with the transistor. So let's look at how this affects the delay of an inverter. So let's assume we want to calculate the delay of this first inverter. That is, I want to calculate the delay between node A and node B. And I want to calculate the delay when B is falling. Now I've designed the inverter for matching rising and falling delays, and assuming that in this technology, assuming that the whole mobility is half that of the electron mobility, I designed the inverter with the PMOS width to be twice that of the NMOS so that I have equal rising and falling delays. The inverter is loaded with another inverter of the same size. And so now I want to estimate the delay. So again, when I want to estimate the delay when B is falling, I'll replace all the transistors with their equivalent RC models. This PMOS is replaced with a 2R by R resistor, a 2C capacitor in its source, a 2C capacitor in its drain. But this PMOS is switched off since we are looking at the falling delay of node B. That's when the NMOS is turned on. And for the NMOS, it has a resistance R, a capacitance C at its drain, and a capacitance C at its source. Now, in addition to the capacitances due to the drains of both these transistors, we also have the input capacitance of this inverter showing up at this node. Right? So the gate capacitance of this PMOS is going to be 2C, and the gate capacitance of this NMOS is going to be a single C. So now if you look at this circuit, what has happened is that this problem statement of finding the delay when B falls is essentially reduced to finding the time constant of this circuit, which has a resistance R and a total capacitance that needs to be discharged of 6C. And where is the 6C coming from? The 6C is coming from 2C plus C and the 2C and C here. So 2 plus 2 plus 1 plus 1, which is 6. Now these two capacitors, that is the capacitor in the source of the PMOS and the drain of the NMOS, do not undergo any voltage change, and so therefore they do not contribute to the timing of the circuit. And so therefore, if you think about the time required for the capacitor charge or the voltage at B to go from VDD to VDD by 2, it has to discharge through this resistor R, and so my T 50% is given by 0.69 tau, where tau is nothing but the time constant of the circuit, which is 6 times RC. Now to simplify calculations, and especially when we look at delays on long paths, we don't worry about this 69% because all delays will essentially be scaled by this 69%. and we attribute a delay of 6 RC to this gate. So this gate has a delay of 6 RC, and the 6 RC is coming about because I have almost a capacitance of 6C sitting at this node. The 3C of the 6C comes from its internal capacitance, and the remaining 3C comes out from the fan-in capacitance of the next stage. Now, since we have designed the inverter in such a way that the rising and falling delays are equal, suppose I wanted to estimate the delay for B rising, the delay is going to be the same as 6 RC because the resistance of the PMOS is going to be the same as the resistance of the NMOS. And that we have done because the size of the PMOS is 2 times the size of the NMOS, countering the reduction in hole mobility. Now let's look at a case where I have not loaded up the inverter. That is, I just have an inverter and I want to look at the delay between the input and the output. Now in this case, even though there is no load connected to the output, we still have a capacitance at this node due to the drain capacitances of the PMOS and the NMOS. And so this circuit reduces using the RC delay model to a resistor R attributed to either the NMOS or the PMOS, depending on whether you're charging up B or discharging B, and a net capacitance of 3C at node B, leading to the delay of this circuit, that is the pull down or the pull up delay, to be 3 RC. Now, if you think about a technology where the hole mobility is half that of the electron mobility, this inverter, which is sized to 1, and this 1 indicates the smallest width of the transistor. So if this NMOS is the smallest transistor, we need to use a PMOS which is twice that size to ensure that the delays are equal. Then this becomes the smallest inverter in this technology, which has equal rising and falling delays. And typically this delay hence is a figure of merit for the technology. And so if this number goes lower, then the delays in most parts are going to go lower. So the delay of this circuit is specifically called out as tau inverter, and it is given by 3 RC. So we sometimes use the units of tau inverter to sometimes talk about delays in a circuit. And that tau inverter is normally 3 RC if you assume the PMOS and NMOS have a width ratio of 2:1. When we do it in terms of tau inverter, we basically make it agnostic to the technology. So let's assume that we have connected an inverter whose size is m times the initial inverter. So this is m into 2 and this is m. So this inverter whose delay I want to measure is driving an inverter which is m times its size. So in that case, the total capacitance at node B is going to be given by the intrinsic capacitance of this inverter, which is 2C plus 1C or 3C, and the fan-in capacitance of this gate, which is 2M plus M or 3M. So the total capacitance at node B is given by 3 into M plus 1 of C. The charging or the discharging resistance in this circuit is still going to be R because of the NMOS or R because of the PMOS. And so the delay of such a gate is essentially 3 into M plus 1 times RC or M plus 1 tau inverter. If I have an inverter who's driving another inverter whose size is M times the initial inverter, then the delay essentially increases linearly with the increased fan out. So if I had only one inverter connected at the output, the delay is going to be 2 tau inverter. If I have another inverter which I connect to the output, the delay goes on to 3 tau inverter and so on and so forth. So here you see what is known as a linear delay model, where the delay in the inverter increases as the fan out increases. To conclude, the RC delay model provides a very quick method to evaluate delays. The delays are normally normalized to the smallest inverter in the technology. The ratio of the PMOS and NMOS are chosen in such a way that we have matching rising and falling delays. So they're normally chosen in the ratios of the mobilities of the carriers. Now the model, and this is an important condition, the model essentially converts a cascade of digital gates into an RC network and make sure that this model only works for delay calculations. You cannot use this model for any DC characterization because that would be wrong. This R and C that has been developed are specifically developed only when the NMOS or the PMOS is charging or discharging a particular node.